matter, in particular inorganic compounds, and we can analyze those by over 20 different spectroscopic methods to show we have a hydrino reaction and a hydrino chemical product. I'm going to go into details, but this particular product was analyzed by electron paramagnetic resonance spectroscopy, which looks at energy transitions of the hydrino molecule, which comprises uniquely an unpaired electron that can align or one way or the other in a magnetic field, and it absorbs specific radio frequencies and going from one orientation to the other. And the characteristics are identical to those predicted theory, and they match nothing known to man. They are completely novel transitions that are characteristic of and identify hydrino. So now getting back to the power. So we have this reaction creating hydrinos, generating enormous power density. It's higher than anything that's capable of producing power today. That is gas turbines and internal combustion engine even, which is very powerful. This is a higher power density than that by potentially up to a factor of 100 times or more. So the plasma creates heat, and the heat can build up pressure, and that pressure can expand to what they call a converging diverging nozzle or Duval nozzle and produce a jet that's a supersonic jet that is very, very highly conductive, because plasma is an ionized gas, plus this particular cycle involves producing molten silver nanoparticles. So it's a molten metal nanoparticle jet, a very high kinetic energy, and that can be converted directly into electricity by applying a magnetic field along one direction and having electrodes in the transverse direction. So something that's moving with high kinetic energy that's conductive going through a magnetic field will cause ions and electrons to go in opposite directions and produce a current. It's extraordinarily highly efficient because the nozzle can be up to 99% efficient. In fact, the space shuttle's nozzle is 99% efficient in converting pressure, volume, thermal energy into kinetic energy. And then once you have a kinetic stream that's highly conductive, you can convert that into electricity, almost unity conversion efficiency. Then those particles coalesce as liquid metal and then are pumped back with an external electromagnetic pump. So it's a very, very elegant design for producing electricity, and it's extraordinarily cheap. And I'll go into the economics of it. So now I'm going to transition to the slideshow and go more over the business and technology. Okay, so we have developed a zero pollution primary energy source. It's applicable to essentially all power applications. We're running now internal field trials at a scale of 100,000 to 250,000 watts, continuously producing steam. And as I mentioned, enormous power densities, about 5 megawatts per liter, and it's capable of much more than that. We've done spectroscopic single shot ignition experiments that we have validated with NIST calibrated light sources at producing 20 million watts of peak power from a 10 microliter shot. So it's just enormous power density. Then the next hurdle was harnessing that power in a continuous manner. I'll come into that in a second. So it's a theoretical breakthrough, and to put in perspective, man's been using fire for 1.5 million years. And at last I looked, in fact, in my furnace at home, we're still using fire. And the rest of society, I mean, particularly in the theoretical realm, has not even hit the first equation required to harness or even discover this new source of power. This invention and this development technology took tremendous amount of investment and time and perseverance. In particular, we have $120 million invested in, decades of work, countless hundreds and hundreds of thousands of man hours into this. For example, we did 6,000 solid fuels with all the thermodynamics, the characterizations of reactants and products, and analysis of all the energy balances, and did thousands of electrochemical cells, thousands upon thousands of analytical, an enormous amount of theory. This is predicted based on classical physical laws, which is the foundation of our modern society. Physical laws are like force equals mass times acceleration, things that you can measure directly, versus, say, quantum mechanics, which is a theoretically postulated mathematical framework that today involves algorithmic curve fitting or regression type analysis with adjustable parameters. So this is exact, and it predicts nature from as a physical, interpretable foundation, from the scale of subatomic particles to predicting cosmological predictions and parameters that are perfectly matched to what's observed today, including the correct value of the Hubble constant and the acceleration expansion of the cosmos. It predicts and solves molecules in exact analytical expression with no adjustable parameters, for example. It was absolutely essential for building upon and giving direction to harnessing this new form of power. So in particular, the chemical signatures, and there are literally hundreds of them that are predicted identically from exact physical laws. So the cell, using that recurring advancement, with different approaches, solid fuels, plasma, thousands of different plasma experiments with Bienecker, Evison, many different types of devices, many different approaches, building and building upon that, building on the analytical, theoretical advances recursively led us to what we have today. And it was a very high bar set for us because it is so disruptive on all fronts, theoretical and on power and technology, that what we were challenged to do is produce something not like flying 100 yards in an airplane, but flying from here to China on a $100 ticket. And that's what we have today. This is absolutely disruptive, ready to go for commercial. It's validated at over 300,000 watts, where we heat it up and without cooling, and at 100,000 watts, running it conservatively under continuously cooled steam production power conditions. The cell comprises a molten metal injector, which injects a molten gallium stream against the counter electrode to complete a circuit where we run through a high current, very low voltage to create the hydrino plasma. And it has a reactant conditioning component where we flow in hydrogen and trace amounts of water to make the catalyst, which is unhydrogen bound or uninteracting, non-interacting or bound to any other species, water molecule, unlike liquid water or even steam where they're dimers, water molecules are dimers. They accept the energy from atomic hydrogen to form this new state. So we use a glow discharge to create atomic hydrogen and this what we call nascent water molecule catalyst. The reaction releases 200 times the energy of burning, and thereby we can use the hydrogen water from water as a source of hydrogen fuel. And as I showed, we have Hydrino in a bottle, the chemical product isolated and characterized by more than 20 different methods or dispositive, and identify it by characteristic signatures or outside the energy range of typical known matter. We have patents worldwide, and I'm going to switch now to the cell. We have that now. I'm going to show you the 100,000 watt steam production. The cell is capable of 200,000 to 300,000 watts. It's been validated by leading experts, but we're going to show in an office building setting in DC, continuous power production of at least 100,000 watts. I'll switch that now.
Good afternoon, ladies and gentlemen, and welcome to our offsite demo here for the SunCell in Washington, D.C. What you're seeing in front of you is the SunCell actually running underwater here in real time in our water tank, and you can see the fantastic energy output that we're actually getting out of the SunCell. So just to give you a brief overview, you can see in front of you here, the SunCell consists of a gallium reservoir that is circulated around the cell, or inside the cell, I should say, with an electromagnetic pump. And this pump allows the gallium to make contact with a tungsten electrode. And the point at which it makes the contact, we can sustain a low voltage, high current plasma to maintain the Hydrino reaction. Now, this energy input that's provided is provided by a DC power supply, but the main energy for the Hydrino reaction actually comes from the fuel, which for us comes in the form of gaseous hydrogen. This gaseous hydrogen actually is fed through a low voltage plasma before it goes into the SunCell, which allows the molecular hydrogen to be broken down into atomic hydrogen, which is then mixed with trace oxygen to make free water, individual molecules of water. This fuel is then fed into this location where this low voltage, high current plasma is being sustained, and that's what results in the tremendous energy output. Now, on the camera feed here, you can see, once we pan the camera up into the tank, you can see the very vigorous steam generation that's occurring. And you can see here this torch that's feeding the fuel into the cell. If you look into the cell a little bit more, you can see the really rapid and violent bubbling that's taking place. And it's even more evident if you look on top as well as down in below through the side window. So if you can. So on the video feed here, you can see the nucleate boiling that's resulting in very large bubbles that is occurring because the liquid gallium inside the SunCell is taking the energy from the plasma, distributing it around very, very evenly throughout the SunCell, which then allows it to transfer the heat out into the water tank that we have here. And obviously we are generating a lot of steam with this product so far. And you can use this either for thermal or have it converted to other electrical or other forms of energy if possible. So if you have any questions, please feel free to leave them in our chat or save them for the Q&A session after the presentation, and we'll be happy to answer them for you. Thank you so much.
Okay, we're back, and so this is the new fire. So this is looking inside of the cell, and we have this as high-speed video, or else slow motion video, as it's commonly known, and you can see the plasma reaction that occurs inside that cell. You can see the molten gallium moving about as being injected inside there, and it creates enormous power and power density. The characteristic purple glow is that's emission of hydrogen, which is being used as the fuel. So reducing atmosphere so we don't get any oxide in there, and there's just very, very trace amounts of oxygen, essentially very negligible, if any, power on a relative basis being created by forming the catalyst, and that's actually external to this reaction chamber where that occurs. So the atomic hydrogen flows in, creates this tremendous power, release of 200 times the energy of burning, And we can look at that spectroscopically and the chemical product and prove unequivocally it's due to the Hydrino reaction. This is what it looks like on the external view. That makes thermal power that we can then harness in terms of heated air. We can turn a turbine. We can make steam. You could do also what they call a Rankine or steam turbine. And then you could also use that plasma for direct power conversion using magneto-hydrodynamic technology. So our current development goals or priorities are to pursue a commercial thermal power source at 100 to 250,000 watt scale using external support from engineering firms, original equipment manufacturers, strategic partners, and outsourcing to manufacturers rather than reinvent the wheel to implement fast deployment of the technology, which is ready to go now. Particularly the first step would be involving commercial packaging that we're working for to outsource to an engineering firm that could produce on the scale of 100,000 manufactured units per year, and then transition to a high volume equipment manufacturer, which there are numerous that can produce devices at that scale. And we do have very high interest in OEMs that want that business. So to execute, we plan to support target, partner, and customer field trials where they would operate the SunCell in their facilities with the goal of establishing original equipment manufacturers, strategic partners, and partnerships, that is, initially with a heat exchanger OEM to make both the steam boiler system and the air heat exchanger, and also an OEM that we would partner with to join the air heat exchanger to a microturbine to produce electricity in first generation electrical power systems. We also are pursuing deals with customers. So you have the manufacturers on one hand and the customers on the other that could really benefit from extremely inexpensive green power. So we're pursuing green power pre-sales, which we think we could become, which would enable us to become profitable. We have developed a 250,000 watt molten gallium to steam heat exchanger to produce hot water and steam, and we're testing that for the corresponding thermal markets. This would operate in the 1 to 15 atmosphere range, very different from highly pressurized boilers that operate at least 10 times higher pressure that are used for electrical production. These would be used for heating applications in buildings, which incidentally, building heat is 25% of the world energy market and about half the thermal market. And also the steam could be used for industrial heating processes, sterilization in hospitals and other hot water heating applications, for example, food processing and curing and the like. So we've also developed a 250 kilowatt gallium to air heat exchanger to produce variable temperature heated air in the range of 100 degrees centigrade to 1,000 degrees centigrade to service the balance of the 8 trillion a year thermal market, which corresponds to half the world's power load or needs, and it would eliminate 1/3 of the world's CO2 emissions. The air heat exchanger can also be mated with a Brayton cycle, which is the same cycle used in a natural gas turbine. It's existing technology. So we're working to establish a partnership with a manufacturer, and we already have a quote for a 900,000 watt combined heat and power CHP system. So ultimately, the goal would be to move to magnetohydrodynamic technology, particularly with this molten metal nanoparticle cycle, this new thermodynamic cycle that enables that technology to achieve very, very high power density, extraordinarily low capital cost. The thermodynamic calculations show that it could be as high as 23 megawatts per liter, which is extraordinary considering that gas turbines may be a couple thousand watts per liter. And because of the high power density and the simplicity and the no moving parts, it could be at least 1/10 that projected capital cost relative to other conventional hardware. So in addition, we're sending samples to independent validators on the existence of the Hydrino product that confirms the nature of our power source and verifies its the foundations of its operability. We have multiple programs in progress, and we have an article already submitted to the world's top journals that confirm the existence of Hydrino that cannot be assigned to anything known in terms of unique signatures shown in electron paramagnetic resonance performed at one of the world's leading scientific universities by a group head who's a world expert. We have other validation projects on Raman and other types of spectroscopy that are in progress currently. So initially we would focus on the $8 trillion a year thermal market, which could be exploited with the system we have now. That system shown in the demonstration does in fact do space heating. To do a common or typical product used in industrial or space heating today, that would be mated to the heat exchanger, and either air or water to form steam would be passed through and serve as a coolant to continuously remove the same amount of power being produced in the cell as heated coolant, being either hot air or steam, that would then be delivered to the load, being the thermal application. Beyond that, we would we plan to transition to the electrical power market, which is about a $3.5 trillion a year market, using first the gas turbine, and then switching to the more advanced technology with superior performance and cost, being the magnetohydrodynamic converter. Given that this is a new form of matter, you can anticipate there's also chemical applications, and there are incredible chemical applications. As a matter of fact, the Hydrino molecule uniquely has an unpaired electron and has unique magnetic properties. It also, because of that unpaired electron, it can serve as an electronic switch, like a transistor or a circuit element and logic element or a memory element. Currently, there's a program involving superconducting quantum interference devices, as they're dubbed to be quantum computing, but actually it's an analytical or an analog form of computing. But that can be transitioned over to, or the circuit element can be replaced by a single molecule 64 times smaller than the hydrogen molecule versus a shoebox-sized device for a single element that has to be cooled to liquid helium temperatures, extraordinary cryogenic requirements. The Hydrino molecule, in contrast, does not require cryogenics and can even operate at very, very high temperature, which enable optical computing at extraordinarily small scale in terms of the number of circuits you could have per unit displacement. Also, there's energetic material markets beyond molecular lasers of extraordinarily short wavelength, like X-ray lasers, magnetic material, magnetic imaging materials, etc. The energetic materials, we've shown with validated results that it can produce 10 times more shock wave effect than TNT per weight. And there's only 1% of the energy coupling to that shock wave. So extraordinary applications in energetic materials, propellants, could be used in mining and construction and the like. Now, Hydrino has been validated by electron paramagnetic resonance, as I spoke of before, because the unpaired electron can produce these very specific radio absorption signatures. There's also rotation, vibration. They're very unique. To give you an idea, the highest energy vibration, which is much higher than rotation, is about 4,400 reciprocal centimeters in the max. And this is at 15,000 just for rotation for the molecular hydrino. It's outside the realm of known matter. And that's true of the other signatures as well. We see an infrared spectroscopy. We see the vibration of the hydrino molecule using electron beam excitation in the ultraviolet, which is extremely high. It's not even in the infrared, where typical molecules rotate and vibrate. We form a new form of gas that has very unique characteristics in that it migrates faster and has a higher thermal conductivity than anything known. And that, again, is characteristic of and identifies hydrino. We can measure its total energy. It's 16 times or 4 squared that of ordinary molecular hydrogen. The energies of vibration rotation are also 4 squared or 16 times that of ordinary molecular hydrogen. We have new chemical compounds we can show by high resolution mass spectroscopy. It's got unique magnetic properties we can show by a technique called nuclear magnetic resonance spectroscopy or magnetometry. We can show new molecules, new behaviors of inorganic compounds with this molecular hydrino absorbed into the compound. We can show energetic signatures that are quite extraordinary, extremely high, selective, high temperatures of hydrogen atoms, shock waves greater than that in TNT, solid fuel energy release, electrochemical power, plasma with no input power, huge power releases in the SunCell, for example. So looking at how the SunCell transfers heat, we have the molten metal injector that's been explained, and it completes the circuit, run a high current, very low voltage, produces tremendously powerful plasma. It warms up a gallium reservoir, and then that gallium is continuously circulated in a loop through the heat exchanger. So it goes through the tubes of the heat exchanger, and it's inside a shell. The coolants flow through the shell. Heat is transferred to that coolant, and then that's delivered to load either as hot gas or as steam. So I'm showing here, this actually has a good schematic of the ignition system that we were talking about before. It has a positive electrode that goes to the center of this tube. The tube is electrically grounded. It serves as the counter electrode. We flow gases in here and put a high voltage, and it causes a glow discharge and creates a typical high voltage plasma to make atomic hydrogen and the catalyst HOH molecule in isolation or without any hydrogen bonding or interaction. Very important. What's unique about this is it turns out that we're running the cells at very, very high temperature. Otherwise, they wouldn't work. And we put them in the water. It wouldn't work because the cell temperature is essentially the external water temperature. Without this glow discharge, what you're seeing today would not actually function. So what a glow discharge does uniquely, for every 1 electron volt, every 1 electron volt of energy the electrons pick up, that's equivalent to 11,600 degrees of Kelvin, or close to centigrade as a unit of temperature, which is extraordinarily high temperature, even though the glow discharge is at the temperature of the water bath, which can't be more than 100 degrees centigrade. So that's a remarkable device in terms of creating reaction conditions to run our reactions. It's actually indispensable. So that atomic hydrogen and catalyst flow into this reaction cell chamber, and we get this extraordinarily high power hydrino plasma. And then we have these electromagnetic pumps that do the injection alike. And then there's this external electromagnetic pump that circulates the gallium through the shell and picks up heat from this reactor, the SunCell, in a continuous manner. So this is showing one of the validations we did with a professor at Rutgers, who's a combustion engineer expert. And in this case, we ran the cell externally from room temperature to almost its melting point. It was glowing like red hot iron. And then we immersed it in this bath, basically dropped it into a 500-pound water, of 500 pounds of water to absorb that heat and warm up that tank and also produce steam. And we had a cantilever, which you can see in this picture here. There's like a lever that is very sensitive to the water weight loss. And then we can measure how much the bath warmed up to determine this energy balance. So we had about input energy, output energy, but the important thing, the input power is about 91 kilowatts. The output power is 433 kilowatts, which gave us 342 kilowatts of power from the Hydrino reaction. And this occurred in a very short period of time. 2 seconds, we put almost 1 million joules of energy. That is a lot of energy. And if it went 2.5, it would have melted down. So there's a great advancement in terms of putting this glow discharge on the cell to process these reactants so we could run it in a water tank and continuously produce steam. So in this validation done by Dr. Dansteele, we were testing and demonstrating the temperature dependence, the current dependence, and the dependence on this glow discharge pre-processing of the reactants to make that reaction. And it's capable of continuous steam production. We ran it, we lost about 25 pounds of water in 2 minutes. So then we run it until the water level gets to the point where it's becoming unsubmerged, and then we stop it, and then we have to refill the water level. But this is a very, very accurate method, just measuring, very simple, just measuring the weight of water that the reaction causes the tank to lose in a given period of time compared to the input energy. So these are some of the parts of the SunCell and the cost. So here you can see the permanent magnets. We put a current vertically here, and then the magnets are transversed to that. There's actually 2 stages to give us extra electromagnetic pumping so we can get better circulation, because at those power densities, the gallium would boil, even though it boils at 2,300 degrees centigrade. It's very high power release. So the molten metal is injected against this counter electrode, the current goes through, the plasma is maintained. And here's this ignition system where we pass the reactants through a glow discharge to create atomic hydrogen and the nascent water molecules. So the total cost here is about $15 a kilowatt. This is for a 250 kilowatt unit. This is the heat exchanger, the shell and tube design, which is very elegant. We looked at a silicon carbide poly block, but this looks much superior and extremely cheap. It's got stainless steel. You might be able to see the tubes, but here you can see tubes that the coolant comes in and passes over. So these tubes have a stainless steel sheath and they're carbon internally, so the gallium will not form an alloy. So it's very compatible with our system. It can run up to 100 degrees centigrade, no problem, because all the surfaces of contact gallium are carbon. Carbon doesn't even boil or melt. It sublimes at 4,000 degrees centigrade, off the charts temperature. But you add this up, you've got maybe about $20 a kilowatt. It's for 250,000 watt unit. So you add that to the SunCell cost, you're about $35 a kilowatt, which is very cheap. And this has no moving parts, and the parts there are in here are all recyclable, including the gallium. So then we engaged the microturbine manufacturer, and they said at volume, you can make this, their microturbine, which is an external combustor design. So it actually takes heat externally and drives the turbine. So most turbines, right where these tubes are, these are the heat exchangers. It's a little bit different design. And this doesn't have a recuperator. These type of devices typically have a recuperator. It means it takes some of the heat coming out of the gas that's coming out of the back of the turbine and captures that heat and recycles it. But this area here would have a combustion chamber. And we're replacing the thermal power of a combustion chamber with these heat exchangers that are powered by the molten gallium circulating from this SunCell. So all in, this is around $258,000 for a 250 kilowatt unit, which could pay for itself in a year in terms of what the power is worth. So it's then you get maybe 20 years or more. So it's a very, very cost favorable scenario. And even with efficiencies, looking at the most conservative scenario, efficiency of the turbine around 30% and gain around 3x, you're looking at a unit that can power itself with no external power. As the gain goes higher, of course, more electricity can be sold using the gas turbine, and we've achieved 10x on the single shots. We achieved 250 times gain from room temperature, and so much higher gain is possible. It depends on how hot the cell is operated. The higher the temperature of the cell, the higher the power and the gain. We've had silver cells that have operated with no input power once they're up to 1350 degrees centigrade. A lot of scenarios there. And if you go to magnetohydrodynamic, it's essentially can be 100% efficient. And I'll explain more about that. So there's really not much issue there with the parasitic load, as they call it, or the load required for the ignition system and the economics of these devices. This is a commercial manufacturer's unit. This is part of a quote we have for a 900,000 watt combined heat and power. So it's got a recuperator on it. It takes the heat from that inefficiency. So the turbine's about a third, 35% efficient. The heat that is not converted into electricity can still be used. Because the advantage of the SunCell over, say, a central generation plant is that you have the heat there. You can't transport heat from, say, Peach Bottom or from Bruner Island or wherever you live and have your power plant. You can't put it in a truck and just ship heat. But when it's on your facility's premises, you can use that heat. And that's the advantage of the SunCell. It's completely distributed and can be run without grid or fuels infrastructure. Totally distributed power and can be standalone, drop in anywhere. Amazon, Africa, which actually has 1 million people, or excuse me, 1 billion people with essentially no water or electricity. So or you can take it to the moon. So it's standalone, which has tremendous advantages. So then we can transition to magnetohydrodynamic. As I was saying, that involves a molten metal cycle. And molten metal was actually the primary objective of the original billions that were spent on magnetohydrodynamic technology to harness coal. Remember, all coal used to be, or all electricity used to be from coal, and now we're transitioning to natural gas. But coal was king in the day of the 60s, and that combustion gas is not, the products that is not of a coal combustion is not electrically conductive. So they added salt, and the salt had to be tremendously high temperature in order to be conductive. Even then, it was like 100,000th of conductivity, or even 1,000,000th of conductivity of what we can achieve in our plasma. So entirely different scenario. And the power scales as the conductivity So they were running 500 million watt plant, for example, in Moscow, and that was achieving about 75 watts per cubic meter. And we're talking about 23 megawatts per liter. So enormously high power density because of enormous high conductivity. And you can extract essentially all the power and energy out of that stream of molten metal as high power density kinetic energy, because at the end of the channel, the metal condenses and can be recycled. You can't do that with conventional combustion gases. It's an entirely different scenario. So the way this works is uniquely, silver absorbs a lot of oxygen, and in the presence of oxygen, silver forms molecular-like nanoparticles that behave gas-like. They don't have the problem of slippage, where gas just slips past molten metal, so you can't accelerate it. So it bypasses the problems of old-style magnetohydrodynamic. It creates a kinetic energy stream that goes through a channel which has magnets and electrodes and converts that kinetic energy into electricity at almost 100%. So now how much thermal energy to kinetic energy is actually captured? It turns out that that can be 99% efficient. The nozzle on the space shuttle, for example, 99% efficient at converting the pressure thermal energy into kinetic energy. That's a lot better than a gas turbine that takes that thermal energy, can only convert it at 30%. So it's entirely much higher efficiency and more favorable. So the other thing is, rather than having recuperators and intercoolers to capture the hot gases in a conventional system and recirculate it to make a closed loop, we end up with the nanoparticles coalescing to molten metal. We pump it back with electromagnetic pump with like 100 watts, not 100,000, almost all the power as you normally have in a conventional gas system. This takes very, very little power to recirculate the propellant as you'd have it, or the working medium of that device. So it can be extremely efficient and enormous power density. So that's the advantages. And because it has such high power density, the cost is very low because you have enormous wattage, and you divide that into the cost per watt becomes very, very low. So we have the engineering done, the thermodynamic analysis done. We've modeled it, and we've done testing on the nanoparticle kinetics and on the oxygen desorption rates and uptake. And it seems like it's all very, very favorable. So this is something we're working on, engaging original equipment manufacturers to develop this technology while we're pursuing the traditional Brayton cycle gas electrical turbine, microturbine converters. Looking at the MHD cost, this gives the breakdown. It's basically the SunCell, the channel electrodes, the channel magnets, etc. And unlike conventional, because it's so conductive, you can use permanent magnets versus superconducting magnets. The cost, even for the MHD system, those components come down dramatically in cost, in addition to the huge power density that's superior to conventional MHD. You can get down to $25 a kilowatt or less. These are the real numbers. These are the costs of the parts, and this is what it adds up to, translates into. So it can be very, very cheap compared to $1,000 a kilowatt for rotating machinery like a turbine. The SunCell can produce AC in addition to DC, because the MHD will produce DC, but you can convert it into DC, from DC to AC using an inverter, which is the same technology used in solar farms. They call it a farm because it takes up a whole farm. So you have to convert it to AC to get it up to high voltage, so you can transmit it over the transmission wires, and then that high voltage is down converted to low voltage, and then ultimately to DC with a whole series of converters until you ultimately end up with DC again at low voltage for consumer electronics and diode lighting and things like that. So with the magnetohydrodynamic, you can just run direct DC right at your house or your building, and you don't have to go through all these cycles, and you don't have the demand charges or the transmission charges and all those losses and all that infrastructure build out, et cetera. Not to mention that it's 24/7, drop in anywhere, doesn't require a whole farm and the transmission lines, and it doesn't shut off when the sun goes down or the wind stops blowing or anything. The other advantage is we'll end up with millions of units. And because of that, you can transmit from SunCell to SunCell. We'll be using it for telemetry, but that infrastructure will already be there that we can make 5G compatible to make a 5G mesh network of telecommunications that could actually in time replace the internet. So you don't have the big server farms and all that infrastructure and big localized power demand, and you eliminate the vulnerability, because right now, if you had electromagnetic pulse, it would knock all that out, or a hurricane or some natural disaster, or if there's some disruption or it's just one node in millions. It will not affect the telecommunication data transmission network. And it can be very private because it's like a series of everybody has their own communication device, like a walkie-talkie in the old days. So it's individualized. Looking at the economics, I got a couple scenarios here to show you. So you got a 300,000 watt unit. So you multiply the hours, the kilowatts, tons of hours, tons of price per kilowatt. So if you go 10 cents a kilowatt, a 300 kilowatt system will earn you $260,000 a year. If you go to some of these other markets like Hawaii or Caribbean or Germany or Japan, and 35 cents a kilowatt multiplier there gives you almost $1 million a year in revenue. So it's kind of a rule of thumb. You've got $1 per watt per year in terms of revenue potential. Another interesting aspect about the economics is that the world peak power capacity is about 15 trillion watts. So if you have 250 kilowatt sun cells and you make 60 million of them, you've got the equivalent of the world peak power. But unlike, say, the ludicrous mode in certain technologies only lasts 10 seconds or you destroy it, this could be continuous, and it isn't costing hundreds of $1 trillion like the proposed Green New Deal. This is actually the real deal where you're looking at hundreds of billions, not hundreds of trillions. So how long would it take you? Well, everything has a what if. So, if you want to look at what is possible, not whether it happened, but if it's possible, whether it's possible or not. So the feasibility of possibility in this is cars is a comparator, 100 million year production. This is no moving parts, very simple parts of it, that there are. So let's say you make 60 million a year at 250,000 a unit. That gets you the entire world generation capacity in 1 year. So that's a very interesting scenario to enact that type of, or deploy that type of program, because then you're instantly without any CO2 production, zero, and no pollution, completely autonomous, and there's no infrastructure to build out. Just the cells. So this is our patent portfolio, and actually it's not complete because we constantly get more and more patents issued. So we are very prolific. We have extraordinary patent portfolio and filings, because it's very important to have good patent coverage so our OEM partners and our customers have the incentive and reward for investing and deploying this technology and building out this tremendous industry that could be many, many trillions of dollars. In fact, as a comparison, just fossil fuels is 10 trillion a year. So it's a very, very huge market potential and creation of wealth that we're ensuring in terms of our patent portfolio. So that wraps it up. We have the validations on our webpage under technology. You can see a number of validations there. There's the more than 20 methods we identify Hydrino in under publications, particularly journals. We have over 100 journals published, journal articles, peer reviewed, and that list is on our webpage. And we have in particular, one of interest is the magnetohydrodynamic cycle. There's a paper there. There's one that's very important is the 20 different methods or more that we show the energetics of the Hydrino reaction and the Hydrino spectroscopy and characterization, and the links to validation reports and other publications are in that article. And there's additional business information. And if you want to follow our progress, there's the What's New section of our webpage where we'll be putting up updates of our development. So I'll take questions, and I thank you for your patience and interest in brilliant light power and our new power source.
Thank you, Dr. Mills. Well done there. And I do want to remind folks, we're going to do a Q&A session here now, and then we'll conclude with Dr. Mark Nansteel, who Dr. Mills referred to in this presentation, who's done some really nice work as an independent validator, and looking forward to hearing him kind of bring us home. So let me run down these questions, and thank you all for putting the questions in chat. Feel free to keep putting them in there, and we'll do our best to answer as many of them as we can. So I'm going to combine two of the first two questions here, Dr. Mills. Help us here. Number one, the amount of silver needed to run an MHD cell or any one of these cells, just help us understand kind of the quantum of silver needed. A little bit of a thought of as how obviously silver is expensive, but just is it fully continuous? Do you not need to replenish it? Just a thought there. So that's one question on the silver. And then the other one, which I thought was a really good question too, is the reason for gallium versus other metals. So maybe you can handle those two first, and we'll go from there.
Yes, silver for magnetohydrodynamic is unique because it forms the silver nanoparticles that we can expand through the nozzle and create the kinetic energy stream. So it's unique in that respect, and also it absorbs up to 25 mole% oxygen, which is released when the silver is heated by the plasma, and those combination gives you the pressure, the drive, the molten or the molten metal equivalent in terms of a high kinetic energy conductive stream through the channel to convert into magnetohydrodynamic power. So the silver we would use is about 1 kilogram. And if you looked at replacing the entire world's power sources, you would use 1 year's production. And talking to the actual suppliers of silver that own the mining companies and the like and produce silver, they do not see it moving the market barely at all because there's enormous silver inventory in the world and it's recycled. So it's a one-time, like 1 year event, and it won't really long-term move the silver markets, in their opinion. And there's a lot by inventory. I mean, when there is a push to try and corner the silver market, silver came out of people's cases and cabinets and they've melted down silverware. So there's a lot out there. So now, in terms of other metals, we're using gallium because it's a molten metal, essentially at room temperature. It's extremely safe. We've had breaches of the cell where the gallium will come out, and we've melted the cell down in that water tank, and it just drips out as molten metal. It has extremely high surface tension and forms an oxide coat that protects it. It's like atomic layer, extremely safe. I mean, it's an extraordinary metal, and it has the highest range between the melting point and boiling point of any known element. And that's very important because the power release is very high and it keeps the vapor pressure low, or the pressure in the cell, because we're running this particular variant at very, very low pressure to sustain the atomic hydrogen and the nascent water. But there are other metals that we could use, in particular metals that don't form an oxide that can't be reduced under a reducing atmosphere, particularly nickel comes to mind that has a higher melting point than, for example, copper. But copper can be used because you can put water in combination with copper and it won't oxidize. So we're very fortunate. Gallium has another unique feature. When it's run under a hydrogen atmosphere, even though there's some oxygen there, even though in trace, it has some water going into that stream, very trace amounts, and that will react with gallium to form a gallium oxide. But you can tell that it's not forming a permanent gallium oxide because we're continuously running current through it. And as soon as it forms, a gallium oxide is extraordinarily high insulator. You would not be able to put a current through it. As we found out, if you put in too much water, that can occur in seconds. So we know that the gallium does not form an oxide under the reducing atmosphere we're running, and we can confirm that by doing X-ray, what they call X-ray diffraction, and EDS. So it's electron energy dispersion spectroscopy. We can tell it's not forming. So that's a very unique feature, but there are replacements like copper and like nickel that will not form oxides. So there's other possibilities there.
Thank you. One question here, just a quick one here. When do you think we might see a working unit in a client facility?
Okay, well, we're going to charge the host of this building for heating the building today. So I hope we satisfied that, checked that box. But then we're working with an engineering firm to put it into a heat exchanger to run it under traditional conditions, which would be we'd put the air through with the blower and blow it out into, like, run it through some ductwork to direct it and distribute it, the thermal, and the same with the water. Like a very elegant water system, heating system I have in my own house. It has the boiler and it has little radiators, and it's very, very excellent and gives you hot water as well. So that's a very, very nice application. So we're working with an engineering firm to package it and then do the 100,000-year volume manufacture. But what we have is a reaction and engineered systems now is very good to do that. We run 100-hour tests, and we're going to put instrumentation to control the gas flows, the ignition voltage and current, the glow discharge, processing the fuels, those parameters, and the flow rates, and the operating temperature, and the operating pressure, and other parameters in that cell that control how much power it makes, and then connect it to the heat exchanger, because they have to balance. The amount of power you produce has to equal the amount of power you're taking away, or else it'll heat up or cool down if they're in mismatch. And you know, my estimation is if it jumped on, if a firm jumped on it immediately, it would be 6 months to get it to the point where we'd have those initial units. And you probably go through another 6 months, another turn of that, and then you'd have something you'd mass manufacture.
Thank you. We're getting a question here too. Is there going to be a paper published in Nature this month?
Well, Nature has a policy that you're really not supposed to publicize. We do have a paper by a leading expert at a top university that has validated, unequivocally put a tremendous amount of independent work, tremendous capability, and great instrumentation. We've replicated that in another facility in duplicate on 2 different instruments. So it's very, very, it's absolute, it's confirmed. It will get published in a major journal. It's earth shattering. The ramifications and importance can't be stated. And we have 20 other methods, and you can see we're making massive power. It's very, very important to the world. It has enormous astrophysical implications as well, because the spectrum we're seeing from Raman, for example, match many of the lines from the diffuse interstellar media that has defied identification with billions of dollars and 5 decades of work. The radiation coming from all over space at enormous power density, 3 times more power than everything in the universe that's been observed combined, matches the spectrum we're getting from our cell. The characteristics of dark matter, which make up most of the mass of the universe, matches the characteristics of what we're making in our cell. And if you ask yourself just pragmatically, if something makes up 100 times more matter than everything we can see, and everything we can see is more or less hydrogen, wouldn't it stand to reason that the stuff we can't see is just hydrogen that just doesn't absorb or emit light like ordinary hydrogen? And that turns out to be seemingly the overwhelming case. So there's many other examples of that this solves enormous amount of problems and the mysteries. So it's very important that the scientific community get this information and take it under consideration. So it will get published. I can't say exactly where, but I'm very optimistic that there should be the information coming out to the scientific community for them to assess it and to further progress with that information.
Thank you. This is a good question and comes from somebody who clearly has been following you over the years. Can you talk just a little bit about photovoltaic and kind of where we are with that process? Has MHD and this new SunCell system, has maybe that overtaken that, or kind of where are you with the photovoltaic view?
Okay, actually, we're running a new design of the photovoltaic before we came down here, and we were looking to maybe show that, but it seemed like it was kind of a little bit of an overload. My take on the photovoltaic is it is feasible in a thermal photovoltaic kind of scenario. And but the difference is the photovoltaic is a triple kind of junction, sometimes 4 junction, where they use what they call 3,5 materials, like gallium arsenide type materials, and indium and aluminum, gallium arsenide, and other things. So, but that's a lot more expense, albeit it can be, say, $60 a kilowatt versus maybe $10 a kilowatt. But then you have the issue of having a cooling system, and at those enormous power densities, you're talking about, typical sun is like a kilowatt per square meter, and they're running 1,000,000 watts per square meter in these high power concentrator. It's called concentrator photovoltaic. And let's say even if it's 40% efficient, which they're much more efficient than the crystalline silicon solar cell, but let's say it's 40%, and they've been higher, but let's say 40, then you have 600,000 watts of heat you have to get rid of, and those cells have to stay very cold. They don't like being at molten metal temperatures. So you don't have much of a heat gradient to work with. So then it gets into microchannel plates and very sophisticated cooling systems that exist. But if it goes dry, even in like a square micron, the whole thing can melt down. So it's very tricky with the cooling and then the capital cost. So it'd be something we would offload to, say, Boeing Spectral Labs, which actually gave us a very elegant design for our type of light source. So it's definitely doable, probably going to do it to an OEM. I'm sure it has applications, but right now the MHD looks super simple and it's really rugged. I don't think we can destroy it, and it's super, super cheap.
This is a good kind of practical question here. As we start to gain market adoption and thinking about, the quality of the service in the field and maintenance and installation, have you been thinking through, the necessary infrastructure needed to help install, maintain the units, and how are you thinking about that?
All right, well, we have thought about that, and we've actually talked to different companies about it, and they are pumped about the business. So they said they can install it in a day. They could pour the pole, preform pads. They just need a local permit. There's no grid connection, so there's no federal regulatory issues there from FERC, Federal Regulatory Energy Commission, Federal Energy Regulatory Commission, and they love that business. They do like $1 billion, $1 billion scale businesses with the utilities, like doing stuff for them. There's the OEMs too, EPC firms. They do the engineering and procurement and construction. And they're pretty hurting right now because the oil and gas industry is in decline and not doing so great. So this would be a really tremendous opportunity for them rather than drilling an oil well or doing a pipeline. Then they could install the sun cells and maintain them. So we want to outsource all that, and they could do the permitting and the construction, and they could gang cells and do the power conditioning and all that things they're doing now for the utility industry or for gas and oil industry, then they could do for the sun cells. So they want that business, and we'd like to outsource that.
Here's a good kind of technical question. How long has a SunCell run at the specific operating power without external power source supporting it?
Well, this is an interesting question because we were running silver. If you go back and look at October 27th post 2016, you'll see that video showing the silver cell with no input power for 10 minutes until it boiled off the silver. So you can run this with no ignition power. Does it matter? I mean, if you go to MHD and you get 100% conversion efficiency and it's running itself on, say, 10% of the output or 20% of the output, the capital cost per kilowatt using the output electricity goes from maybe $25 a kilowatt to maybe $27 a kilowatt. So, and at some gain number, it really doesn't move the needle for the economics, albeit it is possible, and we've shown, and we presented that evidence in video form that it can run without electricity.
But the reality is running it with a little bit, still have a net gain.
You still have plenty of money you can make. Rather than making $250,000 a year, you might make $220,000 or $230,000 a year off a SunCell.
Could you touch on a little bit where we are on the MHD SunCell prototype? Where is it? Does it exist yet? Is it soon? Just talk a little bit on kind of where we are on the SunCell prototype for MHD.
Okay, so we showed a model, and that's actually a scale model with all the components you'd need. And we worked out the electromagnetic pump and induction electromagnetic ignition system, which we have on our webpage. We worked out the induction electromagnetic pump, which is on our webpage. And we worked out, which we published in our magnetohydrodynamic paper about our specific oxygen silver nanoparticle cycle, that the kinetics work out in terms of the oxygen in and out of the silver and on the rate which the nanoparticles are formed. And we are working now on engaging an OEM to prototype and test actual working systems where we would expand the plasma through a Duval nozzle and into a channel that would make electricity. So we're kind of at the let's start engaging the build and testing stage.
Could you talk a little bit about, with the MHD conversion, with the different potential voltages coming out might vary, are you going to need some sort of regulator? And maybe it's more of kind of a question that they've answered themselves, but what type of regulator are you going to need to kind of manage that?
Okay, well, actually, Mark Nansteel did some calculations on the voltages and the currents in the channel. It's actually very short. It's like 6 inches to a foot long to get hundreds of thousands of watts out of this thing at extremely high power. So it's a very small device, and you can take the electrodes, and it depends on what the kinetic energy is and some other parameters of the plasma, how fast it's moving really is as a big factor, and how strong the magnetic field is, and how closely the electrodes are spaced, the separation, the gap, and things like that. And you can take the voltage and you can make it in series or parallel. So in a solar cell, the voltage, the band gap of silicon is, like 1.4. So, it's not, it's a little over a volt. So what they do is they take a whole bunch of them, they put them in series, and they get them up to maybe like 600 volts or same with batteries. So you can always do that kind of situation where you put them in series, make pretty much any voltage you want, and you're trading off high voltage for low current and vice versa.
Just a couple more here, and we'll get Dr. Nansteel to come up here and bring us home. Just one here, which kind of is a nice comment, and let me just give you a little kind of background here. Obviously, with the environment that we're living in here today, politically, et cetera, clearly there's an interest to push forward a green, whether it's the Green New Deal or climate initiative. Wouldn't you think that this would be a good time for your technology to come out, number one, and then number two? The question here is, wouldn't an IPO kind of accelerate this task? How are you kind of thinking about that?
Okay, yeah, the timing is good in terms of the infrastructure, where we are with the technology, and where the priorities are in the energy industry. Couldn't be better. It's a good scenario. So the timing worked out. We've been working on this for 20 years. The world seems like they're in pretty bad shape, and they're basically cutting off. They're standing on a plank, sawing off the end connecting to the ship. So I don't know where we're good. But luckily, we have a lifeboat ready to pull up and solve the issue of what do you do when you push for disruption when there isn't a good safety net. So the timing works out great. Now, the IPO, you got to keep in mind, when you're a publicly traded company, you're heavily scrutinized, and there's a lot of stuff like reporting and accounting issues and all kinds of compliance. And our business team is basically me. And we basically focused on engineering a product, because you can't have a public company unless you have your technology adoption. This, as I explained, was so unbelievably disruptive, and we kept hitting in the wall. It wasn't possible, which now makes an interesting scenario, because if the theory says it is impossible, we have it in a bottle, that represents an inescapable destruction of the theory. So that's inescapable, but now we circumvented that issue and rose above that. So we have it in a bottle, and we have a commercial product, and a product that's more competitive than fire. So now I think the world has to engage with the technology. Now, so that's step one. The next step would be to raise enough money to pay the engineers to make it into a manufacturable product, and to get a management team, because there's all this stuff you have to do to run the business. That is to manage the OEM contracts and the packaging and the initial 100,000 manufacture and the supply chain and the installation and maintenance and depot repair center and all the patent portfolio and the licensing and all the verticals in marine and rail and aerospace and defense and stationary power and thermal power. And you got all the countries, and you got the molecular laser, and you got the electronics business and the energetic materials business, and so forth, and the SEC to deal with, and the equivalents in all the countries around the world, etc. So we need to build the management team get this whole business going. So that's the next phase. We're working on the contracts now with the OEMs, and that looks very favorable for the steam boiler and the air heat exchanger. And we're working on raising this capital to finance those projects and get it into production. And we'll build out the management team. We'll have the greatest company this world's ever seen and go immediately into an IPO once that infrastructure is in place.
Thank you. One last question here, and then we will turn to Dr. Nansteel. Randy, maybe just help us think a little bit about, kind of why does the gap still exist, so to speak? And maybe we're literally closing it as we speak, but the gap between kind of the scientific and the educational community and kind of where we are, when do you kind of feel like we've truly kind of gotten to the other side of this argument and that there is kind of mass adoption, if you will?
Well, that's kind of outside my realm of capability of predicting that, but I will say that we do have Hydrino at bottom. We're welcoming labs around the world, and some people I don't think will ever change their mind. I mean, that's just the way it is, and that's fine. We have Hydrino in a bottle. It's got tremendous applications. It's created by a reaction. We're making hundreds of thousands of watts. There's tremendous business here, and we're just going on that theme. Let's just do business. If people want to do business with us, come to us. We love it. We really want to work with you. If you don't, that's fine. Continue to say the world is like a flower on an elephant's nose and whatever. There's virtual particles and extra dimensions. Your mind's creating reality. That's fine. We're going to go and apply physical laws, create marvelous new technologies, which incidentally hasn't happened in about 60 years, and do great things. And we're looking for partners to achieve that. Okay, so I want to introduce Mark Nansteel, who even the experts say that Mark's in a category by his own, even the top experts. So Mark he's a PhD from Cal Berkeley. He's got a lot of experience in heat transfer and thermal engineering. And he's done some work on our cell, and I'm really proud and very grateful to have him involved with our company. This is Mark Nansteel.
Thanks, Randy. Yeah, I've done a number of validations in the past year or two of calorimetric measurements for the SunCell for BRLP, and the test that we ran today, we didn't do calorimetry for that one because some of the calculations and the data processing for that can be pretty involved and time consuming. Nevertheless, I can talk about the calorimetric measurement because it's really very straightforward. And it's straightforward because we just do two kinds of measurements when we do calorimetry for this device. One is we measure the electrical energy input to the SunCell, and then we also measure the thermal energy release from the cell to the water bath. For the electrical energy input, there's actually three different kinds of energy that we look at. One is the low voltage, high current energy that we use to maintain the plasma. There's also some energy involved in circulating the gallium. That's a pumping energy. And finally, there's some energy required to run the glow discharge, which dissociates the molecules and ionizes the electrons and produces the catalyst. If you add all three of those components together for a 5-minute test, you come out with about 8,000 kilojoules of energy. Okay, that's the electrical energy input. On the other side, there are really only two kinds of thermal energy release from the cell. One is sensible heat, and that's the heat that goes into raising the temperature of the bath water. Much larger component is the latent heat or vaporization heat, and that's the heat that does the boil off. If you add those two things together for the same 5-minute test, you get 25,000 kilojoules of energy. So in summary, you put in 8,000 kilojoules of electrical energy to run the process, and you get back 25,000 kilojoules of thermal energy. 25,000 minus 8,000 is 17,000 kilojoules difference. And that's the energy of the plasma reaction. So it's a very definitive, simple calorimetric experiment because that 17,000 kilojoules is really a little more than twice the energy that you supply. So it's very conclusive. Yeah, the report on the calorimetry is on the Brilliant Light website. Thank you.
Thank you, Dr. Nansteele, and also thank you, Dr. Mills, and most importantly, thank all of you all for joining us today and spending time learning more about Brilliant Light Power. Obviously, feel free to reach out to us with more questions. We'd be more than happy to take some of these questions offline and dig in more depth. But it was a really great time having you all here, and thank you very much.